Okay, so in this question, I'm doing problem number 5, but part C. We already did part A and B in class, so we're going to redo part A and B now when there is friction on the surface that the object is sliding on. So the first part is to solve for velocity when it reaches the bottom of the ramp. So that's this position right here. And we start off with elastic energy, so 1/2 K delta X squared. But we also know that there's friction as it travels over the surface. So the friction or the thermal energy is going to absorb some of that kinetic or elastic energy. So we call that work being taken out of the system. So I'm going to start with a kinetic energy. So this is part C, part A, so part A of C, where I start with kinetic energy. Sorry, the K is throwing me off. This is elastic energy minus the frictional force. And this frictional force is, when it's on the flat surface, mu times mg. And the distance it travels when it has friction is the delta x distance plus my length of horizontal surface once the spring lets go. So this is going to give me my new energy once friction has been absorbed, and that new energy is going to be what's left of kinetic energy when it reaches the end of this ramp. So that's going to be what I'm solving for here. So I'm just going to plug in the values. I have 1/2, that's actually 1/2 is 0.5 times 100K times 0.2 is my delta x squared minus 0.02 times 0.5 times my gravity of 9.8. Delta x and L is 0.7 if you add them together. And then I've got here 0.5 times mass of 0.5, and that's easy because that gives me 0.25. So I'm going to take velocity equals the square root of this whole thing divided by this, which is 0.25. And you can go ahead and plug that into your calculator. And I believe you should get an answer of 2.78 or something close to that value if you had a little bit of a different rounding. Part B is going to be finding how high along the incline the block will move. So what we know is that at the end of this incline, right before it starts moving up, it has a velocity, which means it has a kinetic energy with a velocity of 2.78. So I'm going to start with kinetic energy, and that's going to be from this velocity. And then I know that there's going to be some work done on that object as it goes up the ramp. So the work is going to be any of the forces, so the mg sine theta and the friction, that are opposing the distance in which it is traveling. Remember, force and distance have to be parallel. So my kinetic energy at the bottom is going to be subtracted from, or sorry, it's going to be equal to the energy that is doing work to move it up the ramp. So that's going to be the mg sine theta plus the frictional force, which is mu times the normal, and the normal in this case is a component of gravity, so mu mg cos theta, and that net force is going to be multiplied by the distance, which is what we are solving for. So I'm going to plug in my values. My kinetic energy is 1/2 mv squared, so 0.5 times 2.78 squared is equal to, and actually I don't even want to do that because I realize now my masses can cancel out. So then from there, I can take my 1/2 times 2.78 squared, and set that equal to 9.8 times sine of 30 plus mu, which is 0.02, times 9.8 times cosine of 30, and then that whole thing is multiplied by d. And since I want to solve for d, I am just going to set d equal to, I'm going to turn this into 0.5 times 2.78 squared divided by this whole expression right here, 9.8 sine of 30 plus 0.02 times 9.8 cos of 30, and hopefully we get a distance of around 0.79. The answer key says 0.76, but with a little bit of rounding error, it should be around that number value.